Once again, welcome back everyone to the very last video on parsing that we'll have together. This one is on LR parsing. So last time I showed you this slide explaining that the last thing that we had to see is how to implement CFG parsers. And so last video was on LL parsing and this video will be on LR parsing. Last time I also showed you this slide on historical perspective explaining that basically computers were really slow in the past, and so it was really important to have parsing algorithms that were linear, but also very efficient using only fast data structures. So LR parsing is in many ways the most difficult parsing algorithm that we'll discuss. Don't worry, we won't go into all the gory details. That would be very difficult and it wouldn't be very useful. But my goal is to make you understand how to use LR. So if you ever use a LR parsing tool, you can understand roughly how it works. You can understand the differences between different kinds of LR, and you'll see there's two represented here, LR and generalized LR. And you can also understand the error messages that you get from using these tools. So what's LR exactly? Well, the goal of LR is to parse every deterministic grammar. Another way to say this is that it will parse every context-free grammar that can be parsed in linear time. Yet another way to say that is that it will parse every grammar that it can without ever backtracking. So you might wonder, what's the difference with LL? Doesn't LL also parse every deterministic grammar? Not exactly. LL doesn't do enough. When it sees a character or a token, it has to decide immediately what to do, which choice to take, and it doesn't consider the context. LR, on the other hand, can postpone that decision. So you can see the character and can say, well, let me continue and I will decide later what to do with that. This will become clearer when we see how LR works. On the other hand, LL is much simpler to implement and to understand. You just look at the character, make a decision, and you're done. Let's give some more details. LR, L stands for left to right. That's the direction in which we consume the input. R stands for rightmost derivation. So you remember that LL stands for left to right, leftmost derivation. I use the same example here as I used for LL. In this case, this is a rightmost derivation because we expand the rightmost non-terminal first, and then only we expand the left non-terminal. Now I put in reverse here in bold, and that's very important. In LL, we said that LL is a top-down recursive descent parser, and this parser will always match the left non-terminal first. However, LR is a bottom-up parsing algorithm. And what it will do is that it will simulate a rightmost derivation, so this derivation here, but in reverse. So starting from here, it will move left. There will be a slide that explains this in depth later. So LR parsing is essentially done by a DPDA. And remember that a DPDA is a deterministic pushdown automaton. So it's deterministic because there's only one possible choice, and it's a pushdown automaton, meaning there's a stack. And on this stack, we'll be able to push symbols, terminals and non-terminals. We can also, just like LL, look up the next tokens. And just like LL, we can decide the number of tokens we want to look up. So there's a fixed k. And typically, we'll always use 1. And in fact, we can prove that every LLK grammar can be converted to LL1 grammar. And it's much faster to implement L1 grammar, so that's what is often used. The way the algorithm works is that it will take its current state. And its current state is what's on the stack, in particular what's on the top of the stack, and what are the lookahead tokens. And then it will decide to take one of two possible actions. When it shifts, it will take one token from the input and it will push it onto the stack. When it reduces, it will take a few items from the top of the stack and will reduce them to a single non-terminal. I'm going to give an example, and for this example, I'm going to use the good old JSON grammar. So here it is in expanded form. In particular, the example will be a simple object, and I will show part of this grammar as is needed. So here's the example. As you can see, we are dealing with an object with a simple key. At the start of the algorithm, the remaining input is the whole input, and the stack is empty. The first step, when the algorithm is in this state, will be a shift. So we'll shift the open brace onto the stack. In fact, the first 4 steps are similar. We are going to shift the first 4 tokens onto the stack. So now that's done, the only thing left in the input is the closing brace. And the next step of the algorithm in this state will be to reduce this underlying part into a pair. Let us do that. Now the next step is a little bit tricky, because what it will do is that it will do a reduction, but it will not remove anything from the stack. So from emptiness, it will materialize a t-pairs on the stack. And we can see that we can do this because t-pairs has an empty alternative there. Once we have this, we can use this rule and reduce the pairs non-terminal. And once we have this, we can use this rule and this alternative to reduce the pairs terminal to the pairs interrogation terminal. Once you're here, we can simply shift the next token. And once we have this, we reduce this to an object. And finally, to a value. As you can see, it's not that difficult. You simply do a sequences of shift and of reductions. Of course, the trick is how does the algorithm decide? How does it decide whether to do a shift or to do a reduction? We'll talk about this a bit later. Let's do another example. In this case, we're going to do an object with 2 keys. And what I want to show you here is how it behaves when there is recursion. So we're going to skip the start of the process and we're going to shift these 4 tokens onto the stack. So what's left is the comma and everything afterwards. In this state, just like in the first example, the first action is to reduce these 3 tokens to a pair. The next thing we will do is shift the next 4 tokens onto the stack. So now the only thing left is the closing brace. Now notice something interesting. We said that LR parsing simulated a rightmost derivation. When you hear that, you might expect that when there is 2 pairs, because there's 1 pair here and there is 1 pair there, that it might reduce this first. But actually, it reduces the left pair first. And that's because it does the rightmost derivation in reverse. Okay? So it does reduce the left part first when there is recursion. So the next step will be for this 3 token to be reduced to a pair. And so now we have 2 pairs on the stack like this. Now we are going to do a couple of reductions. The first one will be, just like in the first example, to materialize t pairs from nothing. For that, we use this rule here. So we get this stack here on the right. And now we're going to reduce this to a pairs. For that, we use this rule. Next, we're going to reduce the comma and the pairs to a t pairs. And this is defined here. And finally, we're going to use the same rules as before, so we used it here, to reduce pair and t pairs to a pairs. And this is a state that we're also in the first example, and so now we can do everything we did in the first example to finish. We'll shift the final brace, we'll reduce to object, and then to value. And that's it for that example. So now we get to a slide I promised, which explains the rightmost derivation in reverse. So here's an example grammar. S is AB, AB, then AB is A, then B, then A is small a, and B is small b. And the first line here is the rightmost derivation. I'm not going to read it, but trust me, we always expand the rightmost non-terminal first. What's interesting is the second line. Second line shows a LR parsing process. And so we start on the right with the input. And we'll use the dot to separate the stack from the rest of the input. In the first step, you can see that we shift the small a, and then we reduce the non-terminal a. On the second step, we shift the small b, and we reduce it to the big B. On the third step, we reduce a then b to ab. On the first step, we shift a, reduce it to big A. And on the fifth step, we shift small b and reduce it to big B. Then we reduce those two to AB and then finally to S. So you can see that this is a straightforward LR parsing process. And as you can see, they match. Indeed, LR does perform a rightmost derivation in reverse. What happens if you pass a grammar to a LR parsing tool and the grammar is not LR. Then the LR parsing tool will report a conflict, and there are two kinds of conflict. The first kind is reduce-reduce conflicts. It's fairly rare. It only happens when the same set of symbol can be reduced to the same non-terminal in the same context. And what I mean by that, basically, is after seeing the same input prefix. Another way to say this is that the same portion of input could be matched by different non-terminals. It's an example of ambiguity, and we'll have more to say about ambiguity very shortly. You can create a reduce-reduce conflict very easily by having two rules that match exactly the same thing. That's not very interesting, but a more interesting example is this one. So this is a list of optional words. So the words rule here matches an optional word, and then it repeats by recursion. For any list of words, there are infinitely many ways to match this list because you can match upward as many times as you like if it's empty. So this is massively ambiguous. The second kind of conflict is shift-reduce conflict, and there is a very prominent example of that, and it's the famous dangling else problem. So the problem is this: you have a if A, if B, S1 else S2. So it's important that there's no braces here. You could interpret this in two ways. The first way is on the left, and in this way you say that the else goes with the if B. In terms of LR, this means that when you're here, you will shift the else, and then after S2 you'll reduce the inner if else, and then you'll reduce the whole if. The other way to interpret this is on the left. It is to say that the else goes with if A. In terms of LR, this means that after saying S1, you'll reduce the inner if, and then after saying S2, you'll reduce the big if. This is a real problem that happens in practice. It's a problem that C has and Java has. So to mitigate this issue, the parsing tools will let you decide. They will let you write some instruction that says, well, I want the if to work like this. Or they might also set a default behavior, and typically the default behavior will be that shift takes precedence over reduce. So remember, when we talked about LL, I told you about this tool Gramophone. This tool helps seeing properties of grammars, and it will also tell you the conflicts. So let's see the if-else example in Gramophone. So this is the grammar input. The format's a bit different from what we usually do, but it's very similar. And what you have here is the LR1 parsing table. I will explain it very quickly. This section here gives you the lookahead token. Okay. On the left, you have the state, and the state basically encodes the input that you've already seen. On the right here, we have non-terminals that are at the top of the stack, and this will be used when we reduce something. So let me give you a very simple example. It's not important to understand everything here, but this will give you the intuition. So imagine that we're in state 3. We are seeing the braces. So we look here, and we see that the correct behavior is to shift the token, and then jump to state 7. So we jump to state 7. And in this state, in any case, we will reduce B, either because we see a lookahead else, or we see the end of the input. In any case, we reduce B. When we do that, we go back to the previous state. So this was state 3. And then we look on this part of the table, and depending on what's on the top of the stack, so it's always going to be B in this case, then that's the state we jump to. So we'll jump to state 5. So that's the quick explanation of the table. As you can see, there is a conflict in the table. It happens when we see an else in state 14. The conflict says that we could either shift the else or reduce a simple if form. And so that's exactly what I told you a few slides ago. Let's talk about ambiguity. So I said that ambiguity was when there are multiple ways to parse the same input. Another way to say this is that different combination of rules can match the same input portion. Yet another way to say it is that we are simulating different derivations. Note that a single sentence can have multiple rightmost derivations. Yet another way to think about this is that we are generating different plain parse trees. So those are non-abstract syntax trees that match the structure of the grammar used to match the input. Now, here's something shocking. Ambiguity is undecidable for CFG, so you cannot make an algorithm that accepts any CFG and says whether it is unambiguous or not. But there's a good news. Deterministic grammars are unambiguous. And determinism is decidable, because if you feed a non-deterministic grammar to a LR parsing tool, it will give you a conflict. What we know is that ambiguity implies non-determinism. Right? We've seen what happens when we have ambiguity in a grammar. So this is A implies B, and we can use the modus tollens law from logic, which says that if A implies B, non-B implies non-A, to reverse the implication and say that determinism implies an ambiguity. However, the opposite is not true. So determinism implies an ambiguity, but an ambiguity does not imply non-determinism, which means that they are unambiguous non-deterministic grammars. And here's an example, and this should bring back memory. We showed this example before. We said that this was a grammar that does not do what we expected to do with peg grammars. So it's the language of palindromes. There is only one single correct parse for this grammar. And this is when the A matches the empty string exactly at the middle of the input. So the input is going to be only A, and the only correct way to parse this is to match A to empty in the middle. The only issue is that to find the middle, we need to speculate and to backtrack. So this is an example where it's unambiguous. There's only one correct parse, only one correct derivation, but we need to speculate to find the correct derivation. What is not included in LR grammars? Ambiguous grammars, and that will be the main issue. And then there are some corner cases, like the palindrome grammar, but fortunately those are fairly rare. Let's talk briefly about LR table construction. This is by far the most difficult part about LR. Fortunately, you do not need to understand it. You can use LR without understanding how to build the tables. You know, I put a skull there, but honestly, it's not that scary. It's even somewhat interesting. Unfortunately, I don't have the time to teach you something that is comparatively useless compared to the rest of what I will teach you. And also, you might not share my weird taste, so you might find it quite painful. I said before that there are quite a few variants of LR. So we said that mostly we use LR1, but there's also LRK, which uses more tokens of lookahead. There is also LALR, and LALR has less context than LR. Because of this, you use less states, and so the tables are much smaller. And for a long time, this was the preferred way to implement LR. So tools such as Yak and Bison, they still use LALR, even though these days they can also use GLR or IELR. SLR is like a hyper version of LALR. There is even less context, but as a consequence, it has even smaller tables. IELR, this one is very difficult to pronounce, is not really a variant of LR. It's a way to implement LR that makes it have tables that are almost as small as LALR. So this is really technically impressive. And finally, GLR, which is generalized LR. And this can parse every context-free grammar in ON cube time and deterministic one in linear time. Let's talk about some of these variants to give you an idea. This is not the most important stuff, but it will give you an idea of what kind of restriction these have. So this grammar here, it is LR, but it is not LALR. So let's say the input AEC. So what we do is that we shift the A, we shift E, and then we are faced with a choice. Do we reduce A or F? Both are defined to be E, small e. And normally, you would decide this depending on the lookahead token. So this could be C or D. The trick here is that there is this part here with the B's. You can see that there is an inversion here. So F goes with C and E goes with D, and here it is the opposite. For LR, this is not an issue because LR has the context that we have seen A before. This will be encoded into a state. And because of this, by looking at the lookahead, it will be able to decide. In LALR, this context disappears, and you cannot choose. Now let's look here. This is a grammar that is LALR, but not SLR. And the only difference is that we have inlined the F. So you can see that we have replaced the big F by the small e. Somehow, this works with LALR. It has the context. Don't ask me to explain you why. I'm not sure I understand myself. But SLR does not have the valid context. So after shifting A and E, it will not be able to decide whether to shift D or to reduce E. What this shows you is the nature of the issue. And you can see that the issue is more severe with SLR. Here's a small example of a LR2 grammar. So if you have an input of XYZ, you will shift X, but then you will need to decide if you reduce X to big X. You cannot decide this with a single token of lookahead because the next token is always Y. You need 2 tokens to see if it's Z or W. Now we said that you can always convert a LRK grammar to a LR1 grammar. And so the LR1 grammar that matches this grammar is this one. So this is a very trivial fix. Finally, GLR. The idea of GLR is that at some point we will need to speculate and backtrack in order to match all CFGs. When we do this, we will need to fork the LR stack. To do this, we will use data structure called graph structure stacks, or GSS. This will help us to share as much of the stack as possible, and will make it possible to merge stacks down the line. So I showed a small data structure here, the forking, and then the merging. You have to imagine that there are items here on the stack, and then they diverge, and then they converge, and these items are shared. This ties in neatly with the fact that CFG can be matched by a non-deterministic pushdown automaton, which is a automaton with a stack. Remember that LR can be parsed with a deterministic pushdown automaton. Here it's not deterministic. And also you will remember that when we dealt with non-deterministic finite automaton, I told you one way to simulate a non-deterministic finite automaton was to have multiple bucks in the automaton. Well, here we also can use multiple bucks, but we also need to have one copy of the stack for each buck. In fact, that's exactly how we implement it. So the correspondence between theory and practice is quite neat in this case. So we've seen all these LR variants, but what can we say in terms of expressiveness? So I've put some inequations here. And the meaning of CFG is bigger than LRK means that every LRK grammar is also a CFG grammar. Every SLR grammar is a LLR grammar, is a LR grammar, is a LRK, and it's of course a CFG. We can also compare LR grammar to LL grammar, and so LLK grammars are all LRK grammars. And the same goes for LL1, LR1. So basically, if the number here is the same, then you have the inequation. Interestingly, you cannot compare LA, LR, and LL. There are some LL grammars that are not LALR grammar, and there are some LALR grammar that are not LL grammar. Now, for languages, the inequations are different. Because remember, a language being SLR means that it has a SLR grammar. It may have many other grammars. Some of them may be LRK, some of them may be LR1, etc. But it needs to have one SLR grammar. And we said before that every LRK grammar could be converted into a LR1 grammar. In fact, every LRK grammar can be converted into a SLR grammar. This will completely destroy the grammar, but it can be done, and we have an algorithm for it. So effectively, all these classes are equivalent. They are not, however, equivalent to LL. Finally, we have the same inequation, so not all LL language are LALR language, and vice versa. This was a talk about LR grammar, but since this is our last talk on parsing, I will mention some other general CFG parsers. So these can all parse every CFG. There's the early parser, and if you had the natural language processing course with Pierre Dupont, you might have heard about this algorithm. It parses in O(n) cubed, And it's in fact very popular for linguistics, because in linguistics, natural languages, are very ambiguous. This is a very elegant algorithm. It's probably the simplest general parsing algorithm. Then you have all-star or adaptative LL star. This is used in the tool called Enter, and this is a massively popular Java parsing tool. The algorithm is pretty complex, but if I had to summarize it, it uses LLK, then it goes to backtracking when LLK is not enough. So basically, it sort of works like PEG, but that gives it exponential complexity in the worst case. And so to stay polynomial, because the algorithm is on to the power of 4, it basically builds automata on the fly to perform caching. Then you have GLL. The big idea there is to take the graph structure stacks, which are used to implement GLR, and apply them to LL. So this was, in fact, the last lecture on parsing. And parsing is my specialty. It's the topic of my PhD. So I could talk your ear off about parsing. Unfortunately, we don't have time. We also have to talk about all the rest in compilers. Two things I wish I could have told you more about is how to generate good parse errors. The state of the art of parsers in terms of errors is not great. You'll get something like unexpected token. That's not always helpful. This is an area where it would be great to have more research. Actually, many of you will need to do a master thesis at UC Louvain. So if you're interested to research that area, come talk to me. And if you're someone on the internet and you're interested, well, also shoot me a mail. I have also many other ideas. So if you want to do some research in compilers in general, or in parsing in particular, you're always welcome to contact me. Another area we didn't talk much about is how to effectively build parse trees in all these algorithms that we've seen. So this is usually done with semantic action, and basically what that means is that you just insert code into the grammar to be run at certain points. If your algorithm does not backtrack, this is very easy, because you never have to undo the code that you have run. If you can backtrack, on the other hand, this is a very interesting problem, but we don't have the time. If you want to know more about it, you can always ask me. Okay, so indeed, that's it for parsing. I hope you learned in this segment of the course a lot. I enjoyed giving it. And next time, we will talk about semantic analysis, which is the next logical step after parsing. There will be less theory, although there will be a little bit, and more engineering. Take care and see you all next time.